Well, as mentioned, the core of this international school in this year have two areas. One area is communications, and the other area is sensing, plus several special talks and a very special session at the end of the week. So now we are going to start with the block of talks concerning optical communications. And we are going to spend 2 days in communications, another 2 days in sensing, okay? And then, as you realize in the opening ceremony, we are going to have 2 round tables in order to look for challenges. So now we are going to face the first talk, and the first talk of a total number of five talks, specific talks on communication, on optical communications. And for this track, we have the best people worldwide. If you look for the best people in the world, in the topics we are going to speak in this room, probably you are going to reach the people that you are going to hear in these days. So the first talk is, I can say, a general talk, but a very specific talk in the same way. In the way that Professor Andrekson are going to review what is the situation of the optical communication systems, and he is going to do some approach for what is going to happen in the future. So, Professor Andrekson, I must to say that after to finish his PhD in Sweden, in Chalmers University, he was not the kind of people that remain in his country just studying or doing things in the university theoretical way or in the university labs. In opposite situation, he went abroad, he went to the States, and he spent practically 7 years outside of his own country, in Sweden, just to working in the real field, in companies, very important companies in communications, and very important research labs. So this means that Professor Andrekson not only have the knowledge that everyone can reach studying in books, in papers, something like that, but Professor Andrekson have a very deep, broad experience in the real field. He is the director of a very important lab, fourth lab in his university, and he has many awards for his works. He is a fellow of Optical Society of America, fellow of IEEE, and fellow of the Royal Society of Science in Sweden. And just one detail about the importance of this of his profile: he served several times, 2 times, in the jury of the Nobel Prize jury. So this means that Professor Andrekson is very, very important and key people in communications. So, Professor Andrekson, it's your time. Thank you for coming, and I'm sure that everyone in the room are going to feel very happy with your input. Thank you very much.
Thank you. Thank you very much. I never heard such kind words before. So, thank you again very much. I will show the first slide, which is the most important one first. I'd like to acknowledge all the work from current and former students, as well as 2 companies mentioned here for some of the fibers, special fibers that we have used for experiments. And finally, the funding agencies listed here. So this is the most important slide because it's all about people, equipment and hardware, and about funding. The rest is up to you. So with that said, this is roughly speaking my topical slide. So I will talk about challenges in optical communication. I will talk a little bit about our activities at this center we call FORCE at Chalmers. And then I'll spend a little bit extra time on a special kind of amplifier, which I believe is one very interesting amplifier that can help go beyond current technologies in some way. We'll talk about that later. So just a note, since 1960, 1/3 or so of the Nobel Prizes in physics were related to photonics in one way or another, more directly or basically more indirectly, like the most recent one in the LIGO. That was partly essentially related to photonics, of course. So, but in the context of our world, in fiber communication, of course, this is the most important one, delivered to Charles Cow in 2009, based basically on this seminal paper published in 1966. Unfortunately, he had to wait about 43 years before being awarded this prize, so it took a long time. Sometimes it takes a long time, sometimes it goes quick. So, and then based on all this fiber technology, just a very brief overview, we have really seen an amazing ride over the past decades or so, 3 decades or so. We went from megabit scale, I should probably use this, in the 1980s, early 90s, all the way through gigabit, terabit, petabit, and well, we are not here yet, of course, but the trend is clear. There's a 10x increase in throughput every 4 years or so. This trend is somewhat declining in the past few years. And partly this is simply because I consider the birth of optical fiber communication around 1974, and it's been around for quite some time, so we cannot expect this to automatically keep evolving as it has been doing for the past 30 years. But it's an amazing ride if you think of it. 75 dB of capacity increase in 3 decades. And it's been enabled mostly by 2 things. I mean, wavelength multiplexing, you basically encode data on different wavelengths, and you use that together with optical amplifiers, and you can really get a very high improvement in capacity. Second one is signal processing enabled coherent transmission. That has happened over the past decade or so. So these are, I would think, the 2 most important enablers for keeping riding this amazing ride. So going more forward then, I mean, we do know that traffic grows quite rapidly. The need for traffic is just growing at this approximate rate. And it turns out that the capacity of existing technology, existing systems, is not growing at the same rate. It's growing at a lower rate. So at some point, we will have a real problem here. And up until recently, we have been essentially limited by only hardware constraints. I mean, it's the hardware, the engineering performance of hardware involved in the systems that have been limiting us. And of course, associated with that, cost. But in reality now it's different, as we will see in a couple of slides. We are limited by more fundamental aspects, namely the Shannon limit of capacity. So the question is, how do we think about the next decade? What kind of approaches can we do? Because it's not clear that we can use our current approaches as we have done in the past. Something new has to happen, basically. So the main barriers are really related to these guys. Claude Shannon, there's a picture from, I think, in the early 40s or so, who defined the channel capacity, and of course together with the available optical bandwidth. So it's capacity, how much spectral efficiency you can put into a certain bandwidth, plus the available optical bandwidth. That is kind of the bandwidth capacity limit. And then in contrast to wireless systems, we have the Kerr effect. And this is John Kerr in 1860, which simply says that fiber, like any glass, is nonlinear. So if you increase the intensity of light just a little bit, there will be a tiny but important increase in index of refraction as well. And that plays a very problematic role in optical fiber systems. So this is just a summary of some of the challenges. I'm not claiming this is complete, but we have an issue with capacity in terms of the spectral efficiency that you can reach. In contrast, again, to fiber systems, this is severely limited by fiber nonlinearities, on top of signal-to-noise ratio, which we heard at the break here. We have a limited bandwidth, And of course, we have noise. And noise will limit the reach. And then you have these nonlinearities that causes impairments. And they can, to some extent, be mitigated, but certainly not fully. And then more practical issues, I mean, the cost and the footprint. And finally, a very important topic, I think, these days is energy consumption. In some applications where we use our internet, this energy consumption is becoming a big problem. So this is a list of possible solutions for these particular ones here. So we have spatial multiplexing. I'll talk about that later. And in fact, I'm not going to spend too much time on it because after break we will hear an excellent presentation by Peter Windsor from Bell Labs. So I'm not going to steal the message too much here, but I will mention it because it has to be part of this discussion here, right? Broadband amplifiers, if we can develop or invent broadband amplifiers, that would be great, of course. Now, when about noise, well, you can think of lower loss fibers. I mean, right now, optical fiber losses are roughly 0.2 dB per kilometer, but that's at 1.5 microns. There are approaches where people believe it's possible to significantly lower this loss if you were to move to a 2.1, 2.2 micron wavelength. That requires, of course, the development of a whole new set of hardware. But the current limit of silica may have been reached, but there are other platforms that may do better if you have a 10 to 20 year perspective at least. Same is true for amplifiers. The problem with current optical amplifiers is that they add noise, so they have a noise figure at best 3 dB. In practice, it's maybe 5 dB. So that adds noise. When it comes to nonlinearities, you can consider deploying new fibers that have much lower nonlinearity, so-called hollow core fibers, which I think you possibly will hear about on Friday this week, right? And then you can also try to mitigate the nonlinearities in some way or another. There are several approaches to mitigate the impairment caused by fiber nonlinearities. When it comes to cost and footprint, I think as a high-level statement, integration is key. We need to learn how to copy what has been done in the RF and microwave and ASIC industries for telecommunications. And of course, we are in our community, there's a very, very big effort in integrating optical functionalities on single chips, both monolithically and in a hybrid fashion. So this is something I consider extremely important. When it comes to energy consumption, I think the message here is that we need to do co-optimization. We need to know about not just photonics, but we need to know about electronics, the driver technology, the ASIC technology, and so on, and also more efficient devices. If you do a joint kind of co-optimization here, there's a room for energy consumption reduction very significantly. So with that said, so I'll just go through some of these points in a bit more detail. We have the Shannon limit. This is from one of Claude Shannon's several papers from 1949, illustrating basically this equation here, that the spectral efficiency you can reach is logarithmically dependent on SNR. So obviously, the more SNR, the more throughput you can achieve, or spectral efficiency. This, by the way, assumes a single linear channel, so there's no nonlinearities yet here. But you can notice that it scales pretty slowly with signal-to-noise ratio, right? Approximately 3.3 bits per second per hertz for each 10 dB of signal-to-noise ratio improvement. And 10 dB, in our context, is a huge number. We can also note that the capacity scales with the number of channels you can accommodate within this bandwidth B, which we today do commercially in the context of dense wavelength division multiplexing. But you can also note that the more channels you use to encode data, obviously the number of transmitters and receivers increase as well. And that is causing a potential problem as well. Of course, this equation doesn't say anything about nonlinearities and certainly not anything about cost or power consumption. So that's not part of that equation. So this is a simplistic picture of what happens when you introduce the Kerr effect, right? So you have the linear scenario from the past equation, that's this one here. But in reality, when you increase power into the fiber to try to enhance the signal-to-noise ratio, you will end up with a red curve, something like that. So it starts to bend over in one way or another. The details are not important for this discussion here. But it's very hard to reach beyond a certain value here because of these fiber nonlinearities. So you're kind of stuck with some sort of limited spectral efficiency in fiber systems. So 2 points here. So this nonlinearity is deterministic. The Kerr effect is directly related to the intensity of light. So definitely it's a deterministic effect. So in principle, it's possible to mitigate. The question is if it's practically possible or not. But even then, it does interact with noise, which of course is random, and then resulting in this phenomena to be random as well. So to some extent, in some cases, it's acting more like a deterministic problem, but at other cases and other applications, it acts more like a random situation. In fact, for fiber communication, it acts more random at higher bit rates than at lower bit rates, for example. So I think it's fair to say that with current technology and approaches, spectral efficiency, well, this has already been reached. I mean, we could only dream of such a number 20 years ago when the spectral efficiency was 0.1. Now it's typically 10 for state-of-the-art research experiments. But we cannot expect a very significant increase of that number with current approaches. So what can we do to reach longer? Well, then we have to look at this equation. So it's all about SNR, right? And to make things a little bit more complex, we can include in the SNR a term that relates to the nonlinearity. This was first published in 2001. Of course, it has been elaborated in different ways. But basically, you can include a small term here that contributes, that adds the nonlinearity to this equation. So this SNR now has the linear noise as well as some nonlinear noise. So these are kind of four approaches that you can think of. You can deal with a lower SNR. You can accept the fact that you have a lower SNR, which means that you can live with this if you use advanced forward error correcting schemes. You add some redundancy bits, but that means that you can survive. You can have eventually an error-free system at lower SNR, and that is widely used. And that is also a very hot topic today. Try to understand what is the optimum choice of FEC and so on. You can use more efficient, power-efficient modulation formats like PPM, QPSK. There are kinds of formats that are. It's all about the trade-off, really, between spectral efficiency and efficiency, power efficiency. You can try to maintain a high SNR, and that you can do by using ultra-low noise amplifiers, which I will talk about in a while. You can also think, as we said, lower loss fibers or even distributed amplification. And this is also used today in some cases. It's not very widely used, but that's a possibility. In terms of nonlinearity as well, you can try to deal with them with some signal processing schemes like digital backpropagation. You basically undo the nonlinear transmission with a pretty advanced digital backpropagation. Or you can do all optical approaches to mitigate. And the question is which of the approaches are more effective? And that remains to be seen, I would say. You can try, of course, the final option is to install whole new fibers, let's say hollow core fibers that should have very, very low nonlinearities, and then it can be reduced to a level where it may not be very relevant anymore. But that's a different story. So, okay, so that was, we talked about this term and the reach extension. So basically, the overall transmission throughput is the available bandwidth, the spectral efficiency, which we talked about in the previous slide, and the number of channels here, right? So we talked about that already, but the bandwidth then, to enhance that, we need to think about new amplifiers or try to develop new fibers that extends the low loss bandwidth of or the window of the fiber. Number of channels, well, today, commercially, we use 2 channels already. We use the 2 orthogonal polarizations of light to encode data. So that's a doubling. That's nice. But there will be interesting opportunities to work on spatial division multiplexing to install new, which will require the installment of new fibers that have multiple cores, or you can code data in multiple modes in a multimode fiber. So just look at this spectrum. This is a typical spectrum of the loss in a commercial fiber from OFS. You can see that today, we really only use the so-called C-band. We use erbium-doped fiber amplifiers, which has a bandwidth of, roughly speaking, 5 terahertz, while the low-loss window is about 10 times higher. So there's room for improvement here. Only 10% is currently utilized, in fact. So if you had the opportunity to work with this range, let's say this range here, if you had a spectral efficiency of this number per polarization, a single mode fiber could support well over 1,000 terabit per second. But we don't have it today. The other thing is that if you look at modulation, optical modulation, we do intensity modulation in on-off keyed system that is widely used in optical interconnects. We use phase, and we use sometimes frequency. Well, certainly we use frequency if we consider WDM frequency and polarization. So we basically use all dimensions of light. So the remaining part is really the spatial domain. And today, most people are looking at these two concepts, to encode data in different cores or in different modes of a multimode fiber. I'm not going to say much more about this, but I think the key message here, for this to fly in the long term, integration will be essential. We have to kind of provide a cost-effective scenario for this. And the other thing is it has to be scalable to a large number of channels. We were extremely successful when we went from repeated link to WDM links. And the question is, will this be scaled in reality to the many hundreds of channels that WDM systems are commercially working today? So that is a question that I don't know the answer to. So just history lesson. This is an optical fiber system from the 80s. So you propagated, let's say, 100 kilometers, and then you had optical to electrical to optical converters. So basically a transponder at each yellow box here. And then came the 90s, and we switched to this WDM scenario. You can see how you replaced a huge number of transponders with single optical amplifiers that amplified all the 100 wavelengths at the same time. This is really the main reason why we have such an internet we have today. So this was enabling the very high capacity infrastructure that we have on the planet today. Now, going from this to that made a huge difference. But going from WDM to SDM and WDM, while in this scenario you can see that we can do flexible upgrade, we can add wavelengths both in wavelength or in spatial channels as we wish. So we can upgrade. That's very nice. But you can see the number of transponders does not scale. It scales linearly with the capacity in opposition to the scenario with WDM. So this is my message, that for this to really work in the long term, we need to find solutions to integrate all this in a very effective way. Secondly, as you can see in the red boxes, there are many technologies that have to be developed in order for this to work in a real case. For example, SDM amplifiers. That's not the classic amplifier anymore. You have to amplify. In a few mode situation, you have to amplify all the modes equally, with equal gain and equal spectral features and so on. That's a very big challenge, in fact. So that's enough about that. Well, I have one here experiment from ECOC in Gothenburg by KDDA team in Japan, just to illustrate what's going on in the world today. So they actually encoded data in 114 spatial modes, actually 6 modes in each of these 19 cores. So all in all, 114 spatial channels. And in each of these spatial channels, they had 740 WDM channels. You can just look at the numbers. I forgot. Well, actually, it has 84,000 transmitters then, if you consider them independent. And in fact, at the time, at this post-analytic paper in Gothenburg, this guy got a standing ovation because he said that all of these channels were actually measured individually. So, but the data throughput is amazing. This is the state of the art. This is 10 petabit per second. If you want to make a hair experiment, this is what you'll be doing. But this has to be applied in real life as well. So it's 10 million gigabit in a single fiber. And I'm old enough to be quite impressed by these numbers, in fact. So going back to this curve, this is the dot from this experiment. So here we are today. All right. So a few words about FORCE. We are a center of excellence at Chalmers, but we are a soft research center. And it's an interdisciplinary center among 5 teams in 3 different departments at Chalmers: microtechnology and nanoscience, where I belong, EE, and computer science engineering. And basically, we do much of the photonics, these do much of the information theory, and these do much of the ASIC and electronic hardware in principle. So we have learned to talk to each other. We have learned to co-optimize technology, and so on. This was something that was launched 8 years ago. So the idea is to get a coherent research activity at Chalmers. And of course, the advantage is that we can do things we would otherwise be more or less impossible to do. I will skip that. So these are examples of projects in center. These are major projects, and most of the funding agencies are driven by pure excellence, like the ERC and the Swedish Research Council, and some agencies are also driven by the good of society to some extent. So we have a kind of good mix of projects in that sense. And I'm not going to go through this list, but as you can see, some of the projects are quite long term. So it's anywhere between 4 and 10 years. And this is something we like. We can take risk. We can be a bit more visionary. So a few examples of what we do in FORCE. This is something that we have worked on for a year or two now. So we are now looking at the opportunity to use frequency comb in WDM as well as spatial division multiplex systems. So a frequency comb is basically a set of frequencies that are phase locked. And then we want to encode data on each of these combs and then send them through the system in a coherent fashion. And the nice thing with frequency comb is that it's really only characterized by 2 parameters. It's the center frequency and the line spacing. Everything else is kind of trivial because the lines are phase locked. So our vision is to use such a frequency comb both at the transmit side and at the receive side to make a fully coherent system. So basically, you demultiplex the frequency tones, you encode data, you propagate through your system, and then you have another comb that is phase locked to this one, or that becomes phase locked to this one, and then receive it in classic coherent receivers. And to enable this locking, we can use both digital pilots or optical pilot tones, as I will describe shortly. So the benefits here is that you can get higher spectral efficiency because you have now a system where the frequency drift is essentially absent. There is no frequency drift if you make this right, in opposed to free-running lasers. You can expect more effective nonlinearity mitigation because you have things under control here. I mean, it's less random. There's no random fluctuations of frequencies here. And you can expect reduced DSP complexity. So these are kind of the benefits of this approach. So some examples of experiments. Here we have a frequency comb where there's data encoded in each frequency. There's 20 gigabaud, 64 QAM for you who are interested. There's 50 channels carrying data and 2 channels acting as pilot tones. With this setup, we use these pilot tones to track the frequency offset as well as the carrier phase. So there was actually no DSP-based carrier recovery whatsoever in this experiment. And we achieved a fairly good spectral efficiency of nearly 8 bits per second per hertz and a 10 terabit throughput at 80 kilometers. Now we extended this to a single pilot tone case, so one of these tones were not present anymore, which means that the overhead went from 4% to 2%, and we used a low complexity digital signal processing receiver to capture the carrier phase offset, but the one tone here, that served the purpose to track the frequency offset between the transmit comb and the receive comb here. So with this, we got a little bit higher, 11.1 bits per second per hertz, and a throughput of, well, something like 14 terabit at 50 kilometers. We have also done some recent demonstrations on a concept where we, instead of using pilot tones in an analog fashion, we now use pilot sequences in the time domain, which is another approach. And so we basically have the payload is the white, and then we have the pilot sequences here, which are carrying less complex formats, namely QPSK. So this is 64 QAM, but the pilot sequence then contains about 2,000 bits, and that purpose is to help synchronize, equalize, and estimate the frequency offset. And then in the payload, we periodically also use small single symbol pilots for carrier phase estimation. And so with this approach, we were able to, with under 2.5% overhead, reach these values here as indicated. So for example, at nearly 1,000 kilometers, we reached 8.3 bits per second per hertz, which is a pretty high number for such a long reach. And the throughput, again, was more than 10 terabit. I hope it's accepted because it's not clear yet to me. OK, that was one example. As a whole different example is the fact that, you know, this is old school. When I was a bit younger, we were all only considered about performance and cost, and that was a trade-off. That was well-established trade-off. But now, in some applications, we have to also think about energy consumption. And this makes it a lot more complex. First of all, it's hard because this means that you have to work somehow cross-disciplinary, and you have to learn to talk to each other, and that is a process in itself. And you have to really co-optimize hardware and software. So we are working on this in some applications, and some people have told me that if you look at the electricity consumption of the internet, whatever that is, it will in a decade consume more electricity than is globally produced today. I'm not sure how true that is, but that's what some people have told me.
And 2%.
Yeah, but the bottom line is that when you go to your Facebook and what have you, this consumes about as much energy as the fridge, because there are data centers all across, and if you think about the cell phone itself, it consumes nothing in the context of the applications that you use. So this is serious. This is about right, in fact. So most people are totally unaware of this fact. So as an example, this is in north of Sweden, where it's kind of cold. Facebook put the largest data center in Europe in Luleå. And this, this does not consume, but the overall consumption in 2015 by that data center represented 3% of the global electric supply. That's 3 years ago, and I'm pretty sure that this number is increasing by the day. So we feel that optical interconnects, although they are used to some extent, the optimization and further introduction of optical interconnect is very, very essential here. So this is just one slide illustrating what we are doing. We are working on optical VCSEL transmitters that are very low cost, low energy consuming devices, very suitable for interconnects. Some performance here I'm not going to talk about too much. But at the same time, we are optimizing driver technology. So this is a 4-PAM 56 gigabit driver developed in-house at Chalmers, in fact. So this is the co-hybrid integrated solution. And we have verified this at 56 gigabit at 3.7 bits picojoule per bit, which is, in fact, a record. The target here is to drive this number down to 1 picojoule per bit. I don't know why 1, but it's a magic number, right? So another very interesting topic is phase-sensitive amplifiers, and I'm not sure if I have much time left, but so phase-sensitive amplifiers can provide a noise figure of 0 dB. I hope to be able to show you how that works. And we have identified one interesting application, namely long free space transmission links. So if you think of a link that propagates in free space, it's essentially diffraction limited because of your limited aperture size. So for example, if you have 10 centimeter aperture, simply the transmission loss caused by diffraction will be about 80 dB if you go to the moon. So from a fundamental perspective, it would be great to have an optical amplifier that has a 0 dB noise figure at that point, because in such a scenario, you are fundamentally limited by the quantum noise. And so if you can use the lowest possible sensitivity amplifier here, you will get the best possible link performance, in fact. Of course, if you have a high sensitivity receiver, this can be traded for aperture size and so on. So basically, we are conducting some experiment, as you can see in this table here, where we use, again, I'm going to come back to this in a bit, but we are now at 3.7 photons per bit, which has been published, but we are now at the point where we are approaching 1 photon per bit, which is clearly by far the best sensitivity that anybody has demonstrated. So a few words. How much time do I have? 10 minutes, wow. Okay, that's interesting. So I was going to say a few words about amplifiers. I'm not going to go through all this, but we have some special interest in parametric amplifiers. And why is that? There's basically 2 reasons. Parametric amplifiers is the only known optical amplifier that can reach a 0 dB noise figure, which is in itself very appealing and interesting. So that's one of the driving motivation for that. The other motivation is that in contrast to semiconductor lasers or, let's say, rare earth like erbium amplifiers, where the gain spectrum is dictated by cross-sections, spectral features of the cross-sections of the media used, this amplifier can be tailored to have a spectrum that is kind of man-made. It can be scaled. If you have the proper platform, it can be scaled to any optical frequency, basically. So let's see how this goes. So these amplifiers are not based on simulated emission. They are based on nonlinear refraction that we talked about, right? So what happens here is that you have some sort of nonlinear element, and you have a pump. We operate at telecom wavelength, so we typically pump it at 1.5 microns, and you have a signal. And if the conditions are right at this input, much as these two waves then propagate through the amplifier, much of this energy of the pump will be transferred to the signal, resulting in gain. And likewise, much of the energy will be transferred to a new wave, which we call the idler wave. And if you already start with the idler wave at the input and control the phase relation between these waves, you can achieve a 0 dB noise figure. And we have measured 1 dB, so we are well over the classic quantum limit. There are some features about these amplifiers that sticks out in contrast to, let's say, urban amplifiers. I mean, for example, they are instantaneous, so this is really about the anharmonic motion of bound electrons. So the time constant involved here is a few femtosecond, as opposed to milliseconds in EDFA, which means that, first of all, it means that the pump laser quality has to be very high, but it also enables a very nice range of interesting applications. And the operation is very similar to a coherent receiver, in fact. In coherent receiver, you have the superposition of a signal and a local oscillator. Here you have here in the PSA, in the phase sensitive amplifier, you have the coherent superposition of signal and idler. In that sense, it behaves very much like a coherent receiver. Oh, do I have time? Well, this is the most famous, well, unknowingly famous parametric amplifier, which is not far from here, in fact. I have a video, but I'll skip the video. We can do that later on, perhaps. But this is, I mean, I didn't mention it, but these parametric amplifiers can be based on Chi-3, third-order nonlinear process, but it can also be based on Chi-2, which is second-order process. And so this is kind of like a swing. So you basically pump it at twice the frequency. So it's a second order. It emulates a second order nonlinear. So you pump it at second frequency, and then you kind of get energy into this, and eventually this hits almost the roof here. It's a very interesting video. I'll skip that. I'll skip that. I mean, this is probably the most important slide when it comes to understanding parametric amplification. So I have to show it. So here I have a case, a spectrum, where you have 3 tones entering a nonlinear element, such as an optical fiber. And what happens because of the nonlinearity, in this case the Chi-3 and 4-way mixing, is that the 3 different waves will interact with each other to generate new components. And some of these components will be on top of each other. And you can just, I mean, this omega-3 to 1 is a mixing of this omega-3 plus and minus the 2 psi bands generated by the Kerr effect. So they add up here and here. But some add up constructively and causes eventually optical amplification. In general, this is the number of tones that you will generate. So in this case, with 3 inputs, you get 9 outputs. If you have 10 tones, you will get something like 5,000 tones. Of course, in reality, that's not going to happen. But the key point here is that this term here is providing parametric gain. These additional contributions add up coherently and can make very significant gain here. We see up to 70 dB of gain, for example. And then you generate this main idler over here as well. Okay, so a few things about this to happen. So first of all, this is a process where there's no energy exchange. So the energy remains the same. So you can think of it as you have two pump photons hitting a virtual state, generating 2 new photons at different energies, according to the spectral picture here. So you have these 2 tones that mix with the present incoming signals, and then you add photons here and here. So this is how you get parametric amplification. And this also illustrates that the energy has to be conserved. You also have to conserve moment, which means basically that the velocity matching has to be very good, near 0, for this to happen. And also power, by the way, is conserved here. So it's pretty much a conserving system. This is a so-called non-degenerate dual pump case. There are many other cases that we can discuss. For example, you can have a single pump containing 2 photons. So the 2 photons then are transported from the pump to the signal and to the idler. As you can see by this picture. This is an approach which is very compatible with multiplexing, so you can imagine having several signals here and several idlers here. But another case is where you have degenerate signal idler, so the signal idler is the same, which means that only one of the waves is carrying data. So now you have two different energy pump photons which generate equal energy signal photons here. And that means that the signal here has to be in the center between the two pumps. I have to skip a few slides, sorry. But this is all in the distributed, yeah. 5 minutes? 10? Oh. Okay. I mean, this illustrates the need for phase matching. So basically, the velocity of the involved waves in any of these processes have to be matched. So if you don't have good velocity matching, the power indicated in red here, I believe, is not adding up. But if you have sufficient phase matching or even perfect phase matching in green, you start to see some growing signal here, which means that you have amplification. It's very, very straightforward to solving the nonlinear Schrödinger equation to get to this simple expression. Right, so that's phase matching. So now we can look at some specific amplifiers. This is the first case, phase insensitive, we call it. I have to state again, Fourier mixing is always phase sensitive, but you can implement it in a way that it becomes phase insensitive of the input signal wave. So this gain does not depend on the input signal phase, just like an EDFA. So from a black box perspective, it's like an EDFA. It so happens, you can show mathematically, that the generated idler will adjust itself to sustain the proper phase matching condition, at least of first order, which is kind of amazing. But that's what happens, and you can get extremely simple expressions for the gain here. And this is related to the fact that there's no material, there's no transition elements or anything like that. This is really dictated by only three or four parameters, namely the pump power, P, the gamma, which is the nonlinearity, and then some other parameters which relate to dispersion. So delta beta is basically the dispersion characteristics of the nonlinear element. So extremely simple expression. So the maximum gain you can achieve is given by this expression if you pump it with one pump, and that is the case with two pumps. And you can see the only thing that matters is the nonlinear phase shift. So gamma, P, L effective, basically. So the length of the fiber that you use in our case. So if you can reach a pi phase shift, nonlinear phase shift, then you have roughly 20 dB gain. It's very, very simple. And of course it works. These are all data just illustrating how it behaves. Just supporting the theory with the experiments. Move on to the phase-sensitive case. But in this case, you have to have an idler at the input as well. So you have the signal, idler, and pump. And there are two different cases here. So now it's a bit more challenging because now you have to really make sure that the relative phase among the involved frequencies are matched accordingly. So this is the kind of term that you have to track and sustain to pi over 2. If it's pi over 2, pump will flow from the signal from the pump to the signal in an idler. If it's minus pi over 2, it will flow the other way around, in fact, and we have seen that. So this has to be maintained. That means that you have to deal with frequency and phase-locked waves at the input of such an amplifier. Otherwise, or somehow control the phase. Otherwise, it's not going to work. But if you make it work, okay, we come to the results. I'll skip a few slides here. This is the kind of simple theoretical foundation. And all I want to say here is that the output field is simply a superposition of the signal and the idler component. They are coherently added to each other, in fact. So it's very much like a coherent amplifier, and the same is true for the idler, of course. And you can analyze this, for example, if the signal and idler at the input are entirely equal in terms of power and phase, the output phase can only approach multiple of pi. So we are talking about squeezing. This is a simple way of squeezing light, in fact, in the phase, in one quadrature. We can also note that the gain of such a phase-sensitive amplifier is 4 times higher than the gain of of the phase-insensitive solution, and that is simply because, again, this coherent superposition. So you have two fields, 1 plus 1, square it, you get 4. If you have non-interferometric addition, which is noise, 1 plus 1 is 2. So you basically, you reach higher gain in the PSA than you do in the PIA. But it's a bit challenging because it requires this phase control, as I mentioned. But the squeezing happens, of course. This is a case we did several years ago now, and you can see that if you have no phase sensitivity, you get a constellation diagram that occupies the circle here, but as you go to a PSA mode, you basically get the squeezing. So the light at the output can only be in one plane like that. Okay, I'll skip these slides there. So I think this is kind of important, but so let's talk briefly about noise. You always have vacuum noise in any system, right? So this is the level that you have at 1550. So if you look at a phase-insensitive amplifier, you have the vacuum noise at the input. At the output, we are talking about the transfer matrix that basically describes this coherent superposition, including noise. So this is the amount of noise you get here. And if you look at the power, you see that you have the vacuum noise here, and you get this amount of noise at the output. Now, if you go to a PSA, it's exactly the same. So you have the same amount of noise, in fact. So it's not like a noiseless amplifier per se. It adds the same amount of noise. So, but now we add the signal. And this is where it becomes interesting. You have the signal here, and you get the gain. So you have the gain times the input signal here. But for the PSA, now we split the power into two different waves. So signal wave has half the power, the idler wave has half the power, and yet you get 2 times GP in. So in fact, the coherent addition of the signal and idler gives 6 dB higher gain than in a PIA. So we know that the quantum limit for PIA is 3 dB. And so based on this, we have 6 dB higher. The quantum limit of PSA is actually minus 3 dB. So we have a noise figure of minus 3 dB. It sounds great, right? But it's not entirely true because you cannot ignore the presence of the idler. So if you count for the idler in this, then the actual noise figure is 0 dB. So the purpose of the idler here in the process is simply to participate in the amplification, and it's not needed after the amplification, in fact. So it's just a tool to reach this 0 dB noise figure. And this has been demonstrated experimentally. And I need to mention also that these amplifiers can be quite wideband. So this is an example where we look at the spectral features of such amplifiers, and we reach gain across 170 nanometers, which is quite a bit larger than current EDFAs, for example, and yet quite decent noise figures, well below 3 dB. And in some applications, we can use this for optical sampling. So we have a highly nonlinear fiber here. This is phase-insensitive mode, and we use it not in CW mode, but we have a pulsed operation, pulse source here. So it basically takes a stroboscopic snapshot of a signal here. And then we filter out the idler at the output. We have some amount of gain here. Filter out the idler, which means that it's kind of like equivalent time sampling approach. And this is what you can do with such a system. You can sample data at extremely high speed. This is approaching terabit, and you can do fun stuff with that. You can also add multiple gates, so as to actually go to real-time sampling. With this approach, we were able to capture the first real-time 40 gigabit data. This is 10 years ago. But in principle, if you take current technology and scale it to 4, as we did here, it's possible to make real-time sampling with terabit rate today, in fact. And finally, you can add coherent detection here, so you have a local oscillator on top of this sampling approach, and then you can capture constellation diagrams with extremely high fidelity. But the real application, I think, to discuss is how can you, what benefits are included if you transmit in a fiber system instead of EDFAs using PSAs. See, you can already see the drawback here is that you have to propagate the idlers through the system and then only dump it at the receiver. So you basically lose some spectrum here. That is the drawback. But the benefit is that you will have a 6 dB noise figure link advantage, link noise figure advantage, which can be used to increase reach or increase the spectral efficiency. It's also a bit challenging because of the need for pump recovery. At each stage here, you need to recover the pump, and you need to care about dispersion and polarization and so on. So let's look at capacity here, because there has been some debate on this topic. So we know that the 6 dB increase from SNR can improve the spectral efficiency or increase the reach by a factor of 4. We have seen that also experimentally. But this comes at the expense of the idler, which means that you have to suffer 50% in spectral efficiency, and that's a big question mark. It is both yes and no. In fact, you can just look at the formulas for capacity and look at the two cases with PSA versus PIA. And yes, for high SNR, for very high SNR, you are approaching a factor of 2 loss in spectral efficiency. But in fact, the opposite is true. If you approach very, very low SNR, you gain in spectral efficiency equally. So if you operate around 3 dB of SNR, these two approaches are equal. And the free space stuff that I talked about earlier, we are operating under 3, in fact. So in that sense, this is a solution that is more capacity approaching than a signal frequency solution. And by the way, this is not including the nonlinearity mitigation, which I will talk about if I have time. I will skip some practical issues. But in fact, it turns out that you can also mitigate nonlinearities in this approach. So you think of the signal, and then you have some sort of delta, which is the nonlinear distortion. And the same holds for the idler, because they sense the same system, basically. And in the coherent superposition, these two components cancel out, and you have recovered the signal. That's a first-order approach, of course. And it requires anti-symmetric dispersion and symmetric power. But we did some simulations just to illustrate. This is part of a 16 QAM, where you have signals here, and idler is phase conjugated here. And this is what happens at the output of a fiber. You can see the nonlinear distortion. And then finally, you do the coherent superposition, and the light blue dots are indicating the improvement that we observe numerically. We also observed that in an experiment. I'll skip through here. We not only observed a signal-to-noise ratio improvement by having low-noise amplifiers, as indicated here, but we also observed very significant reduction in nonlinearity impairment. So all in all, with this, we can enhance the reach, transmission reach by at least 4 times. We have also seen even up to 5.6 times reach extension with this approach. So a factor of 4 comes from the linear aspects, and the additional come from the nonlinear aspects. Now, this is my last slide. So this is a parametric amplifier. You can see the problem, right? It's a couple of spools of fiber here, which are interspliced with inline isolators to avoid SPS. And they also strained to avoid SCS. And the actual setup is kind of big. So it's not anything close to an EDF8, not today. So I think a message here is this is fun and this works, but we need to look at other platforms that can be much more compact, and just list a few here. And we'll talk maybe in the discussions tomorrow about these. And this can have some dramatic improvement, not only size, but also possibly improve the noise figure, because we are limited by some internal Raman scattering in the fiber here. You will have lower latency. You have potentially many significant improvements that you can expect by finding the proper platform. It's not clear which is the proper platform today, though. And one key challenge in this context is to have this nonlinear phase shift as large as possible. So with that, this is my final slide. So spatial multiplexing integration are very important to continue this amazing ride in capacity. And I hope to hear more about that after lunch. I think broadband amplifiers and frequency comms can play essential roles in future systems. Energy consumption is becoming increasingly important, especially for interconnects used for data centers, supercomputers, and other applications. And then I spent quite some time on fiber amplifiers, because I think, this is a promising kind of amplifier that needs to see more attention. So far, we have demonstrated low noise, high bandwidth, record sensitivity, and reach extension. And this ultra-fast response enables many interesting applications, including the optical sampling that I discussed. But again, other platforms deserve attention. And also the final note, these so-called noiseless amplifiers, I'm sure, can find non-telecom applications. While this is all about telecom, I think there are many people and scientists in the world that would like to have a 0 dB noise figure amplifier in principle. So this is part of why this is exciting to me. So thank you very much.
Thank you very much for the very, very interesting talk. And everybody realizes integration is a key issue for these topics and for many other topics. integrated optics, we need new advance. I remember in the period of what Professor Andrekson and myself was finishing the old PhD, similar period of time, we were working in integrated optics. And at that time, lithium niobate was the key material, but today is still key material. But the great trouble in order to do the integration is that in this kind of material, we need very long aspect ratio. So with very long aspect ratio, it's very difficult to do the integration of many different devices. So now with new theories, probably this both for telecommunication and for sensing, integrate optics, integration of the devices and systems is going to be a key issue as Professor Andrekson put in the final notes. So thank you very much again. And now it's time for questions. Please. One question from the middle of the room.
What's the relationship between the phase matching condition in the four-wave mixing and the phase sensitive amplification? Is it the same thing or the different?
I didn't quite get the question. What is the difference between phase insensitive and phase sensitive?
Phase sensitive amplification and the phase matching condition.
Okay, so if you operate in phase insensitive mode, you don't have an idler at the input of the system. And idler will be generated locally in the fiber. But in a phase sensitive solution, you have three waves at the input. You have the pump and your signal and also an idler.
Okay.
And this allows you the flexibility to decide if you want parametric amplification or even parametric attenuation. It's all about controlling the phase of these three waves that need to be involved.
But I think the phase matching is the match of the wave vector of different wavelengths. What's the relationship between
Okay. So phase matching is important in order to preserve the proper phase relation. If you have some dispersion, slowly the transfer of power from the pump to the signal idler will decay, and in fact, at some point, energy will start to flow back. So phase matching you control by having a dispersion property of your nonlinear element that's appropriate. So basically, low dispersion is key.
Okay.
So it's important to have very low dispersion in the nonlinear device.
Okay, thank you.
Okay, thank you. We have another questions in the last part of the room. Don't worry, everyone we are going to have time. Okay?
Thank you for the very interesting talk. So as you know, there's a great interest in thulium doped fibers and thulium doped fiber amplifiers. So do you, which will help us, go beyond the conventional erbium window. So do you see TDFAs as a, practical solution to future communication problems, or you think maybe some other technology will?
I think EDFA is an amazing device. We should be very thankful that the erbium transition coincidentally overlaps with a low-loss window in telecom fiber. That's an amazing natural coincidence. And it turns out that it's extremely efficient because of the very long lifetime. And I have to say it's hard to believe that anything can beat that in that context. But given that, the drawback, as I think I pointed out, is that it's pretty limited in its bandwidth. And these other thulium and other approaches have shown that in fact, 100 nanometers or more is definitely possible. But what it means is you have to shift wavelengths from 1.5 to 2.1. And that's a huge step to take. And we my personal opinion is we need to wait for the fiber technology to develop to the point that they have lower loss than the silica fiber. Then we can start talking. And it's been promising for a number of years, but there might be some breakthroughs on the horizon. And if that happens, then we'll have to look at what does it buy us to make this very huge switch from 1.5 to 2.1. So in my world, it's not happening in the next 10 years, and I might be retired by that time.
Thank you. Thank you very much.
Another question in the middle of the room.
So in this slide, you brought the fiber optic parametric amplifiers, 170 nanometer of bandwidth. But what about the dispersion of silica in this huge bandwidth?
Well, dispersion is. Are you thinking about the bandwidth of the amplifier, or are you talking about the transmission fiber itself? Because I mean, okay, so the dispersion in the transmission fiber, I would say, is not a problem. You can deal with that with the digital equalization, right? So it's dispersion in the fiber used to be a very key limitation 20 years ago. Now it's not anymore. So in terms of transmission, dispersion is a non-issue, I would say. You deal with that in coherent detection, after coherent detection. When it comes to dispersion in the nonlinear element for amplification, that might be a different story. But again, it's the same answer that I said before, that it's a man-made solution, and you can probably invent some very interesting property to flatten the dispersion across very broad frequencies. That has been done already many years ago, in fact. But it's an open question to what extent this is needed and so on.
Any other questions? Yeah, please.
Have you ever tested such amplifiers in a multimodal regime?
No, we have not for spatial division multiplexing. We have not experimentally tested, but we have some theoretical work where we try to see whether it's possible to use a single pump to amplify parametrically 4 different modes in a multimode fiber, and we have some data I can show you, but it's all theoretical, and we have kind of optimized the geometrical structure of the fiber with some practical limitations on germanium content and so on. And it seems that, yes, you can use a single pump to amplify parametrically at least 4 modes. So we're looking into that topic.
Thank you.